So for chapter 7, we are going to expand on the circular motion topic just a little bit, and now we're going to look at gravitation. And we're going to look at planetary orbits, things that move in a circular pattern. We're going to look at satellite orbits, things that orbit around the Earth, things like that. But this builds off of our circular motion portion of chapter 6 a little bit. Okay? So we're going to start with something called Kepler's laws. Okay, Kepler's laws is the very, very minor part of chapter 7. We're going to cover it quickly here at the beginning. But I'll tell you, it's not really the main focus of what we're looking at in chapter 7. Okay, but Kepler's laws kind of introduce us to this idea about planetary motion. Okay, so they're called Kepler's laws of planetary motion. They give us a pretty detailed description of how these planets move. Okay, and what their orbits look like, how they move in reference to the sun, the shape in which their orbits are found, lots of stuff like that. It's a pretty simple equation, but it tells us a lot about what that looks like. Okay, he's got a few laws, so I'm going to go over, I think, 3 here, maybe just 2. I can't remember off the top of my head, actually. His first law tells us that each planet has an elliptical path with the sun at one focus point. So I'll show you here in a diagram that he has a couple focus points drawn within this elliptical path, and the sun will always be located at one of those points. Can anybody tell me what the shape of an elliptical is? Like, what's another word for it? Yeah, like an oval. Good. An elliptical is kind of a stretched circle or an oval type shape. Okay? So it has an elliptical shape, and the sun is at one of these focus points. Okay, so here's kind of the diagram of what I'm talking about here. We see this elliptical shape, right, a stretched circle. And he's developed what we call 2 focus points. Okay, so at any time this planet is rotating, you can find the sun at this at a focus point, right? And the focus point has to do with the angle it is from the planet, the distance that it is from the planet, and it has to do with a relationship between the period of this planet's orbit and the radius on which it is from the sun. Okay, and I'll kind of show you the equation that goes with that. But he's developed this idea that at any point in a planet's orbit, they can locate the sun based on those focus points. Okay. So the second law says each planet moves so that an imaginary line drawn from the sun to the planet sweeps out equal areas in equal periods of time. Okay. This is a little wordy. Okay, so get written down in kind of an abbreviated version, and then I'll show you what we mean here on our diagram. So based on the sun being at one of these focus points, right, this would be a focus point right here, our planet is orbiting in this direction, right? We're moving in the counterclockwise direction. What it's saying here is that as this planet moves through its orbit and reaches this point, it covers this purple kind of, I don't know, pizza-shaped area of its path, of its orbital path, right? And we see this line drawn from the planet to the sun. It covers this area, okay, in a certain amount of time. But his focus points allow us to see that if we're at a different spot on our orbit, let's say we're over here and we're traveling still in the same direction, if we draw a line from our planet to the sun, this area is going to be equal to this area. Okay? And it's the same thing over here. A shorter period of time, but further from the focus point gives us the same area. So all 3 of these kind of relationships and the ratio between the distance from the sun and the period of this guy's orbit, this planet's orbit, are going to give us this relationship based on this focus point. Okay, and I'll show you the real equation for that. Okay, so his third law gives us the actual equation that gives us the relationship here. Okay, so his third law is the ratio of squares of the periods of any 2 planets revolving around the sun is equal to the ratio of the cubes of their distances from the sun. That's really wordy. You can just write down the equation, okay, for the third law. It's just spelling out the equation for you. Okay, and I have the same equation written two ways. Okay, either way is fine. It makes no difference to me. Okay, I would choose one of those to go on your equation sheet. Okay, you probably don't need both. One of them is probably fine. So the only difference between this equation and this rewritten version is that in this equation we compare the periods of each planet on one side and the radius of the planet on the other side, or the distance from the sun on the other side. Here we put all of planet A on one side and all of planet B on the other side. We just rearranged his equation to give us a little different look. Okay, it makes no difference which one you use. They're going to solve exactly the same. But essentially we're going to be able to compare the period and the radius of two different planets based on that principle that they're going to sweep kind of the same area over the same amount of time. Okay, that little diagram that we looked at last slide, that allows us to compare two different planets on their orbit to see what their distance from the sun is and how long it takes them to complete one time around the sun. Right? The period in this case is how long it's going to take to make one complete orbit. Right, so what is the period of the Earth? Yeah, a year, right? A year. It would take a whole year for them to orbit the sun, right? It's not just the spinning on its axis. It would be a whole year. Okay. All right. Let's go ahead and try one here. Determine the distance from Mars to the sun by using Earth as a reference. So in this problem, does it matter if the period is in years or in seconds? Do you think it makes a difference? In this problem, it doesn't, right? We're just looking at that ratio. So since there's no constant in this equation that needs the units to be specific, right, there's no need for us to convert that years to seconds. Okay? So we'll go ahead and set this up, RMS. And we could just go ahead and cube the numerator and the denominator, right? Algebraically, doesn't that work? If we have a cubed outside the parentheses, can't we just cube both of those? Okay, because we're going to have to end up separating those. So I'm going to go ahead and get rid of that parenthesis and go ahead and put those numbers in here. Okay, the radius from the Earth to the Sun is 1.50 times 10 to the 11th, and that should be cubed as well. Okay, the period of Mars is 1.88, and we're going to have to square that. What's the period of the Earth in years? Yeah, 1 year, right? 365 days, so 1 year. Okay, does that make sense? Seeing where those numbers came from? Okay, so algebraically, do you know what we're doing here? Yeah, you can cross multiply and then you would end up dividing by 1, which would be fine, right? Cross multiply and divide. But then at the very end, what do you need to make sure that you do? cubed root. Do you know how to do that on your calculator? Hit math, okay? On your calculator, you should hit math, and I think it's the third option. 2.3 times 10 to the 11th meters. Okay, so algebraically, this is what I did. 1.88 squared times 1.50 times 10 to the 11th, and then I cubed just that. So you might have to do that in parentheses. Okay, we don't want to cube 1.88 squared times 1.5. We want to cube just that 1.5 times 10 to the 11th. So make sure you're being careful there. And then math cubed root that answer. Okay? Yeah. Okay. That's all that you'll need is that one equation. We don't use it that often. I want to show it to you in case we do need it. Okay? So now we're going to move on to Newton's law of universal gravitation. Okay, or universal law of gravitation, however you want to say it. And this has to do more with the Earth and how things are gravitated toward the Earth, right? The last one was about the sun and all the planets. This one is really more focused on the Earth and how things are pulled to the Earth. Okay? So Newton understood that the moon kept a really circular and a really symmetric path around the Earth, and it kind of got him thinking as to why would it do that, right? If he understood Kepler's laws, he kind of thought that it was more of an elliptical path. So what keeps the moon in this circular path around the Earth, okay? So you don't have to write all this part down. I'm just kind of talking through how we get through this idea of gravitational motion, okay? So what he started looking at was the gravitational force on the moon by the Earth, that's exerted by the Earth, and he compared it to what was the gravitational force of objects on the Earth, right, to see if there was a difference in gravitational force when you get farther and farther away from the surface of the Earth. Okay? So this is the universal law of gravitation, and this is the part that I would like for you to have down, so this last kind of paragraph. And it's a scripted kind of definition of what the universal law of gravitation is. Okay. So we wrote the definition. Did we think about what was happening while we were writing it, or did we just write it? Okay. So what I want you to start thinking about here is it says every particle attracts every other particle. Okay? There is a gravitational force between every single particle on Earth. Is the gravitational force ever enough to make two things kind of start randomly sliding together? No, right? I don't like randomly start sliding over toward my desk because there's a gravitational pull, right? There's a gravitational pull between the Earth and every object, and the Earth's mass is so large that it trumps every other gravitational pull, right? Because that's never going to meet the mass of the Earth. Okay, there's a gravitational pull between the Earth and every single object, but there's also a smaller gravitational force between every single object on Earth and every other object. Okay, so any particle has a gravitational pull to another particle, but it's not going to be great enough to overcome the gravitational pull by the Earth. Okay, so that's why everything is pulled toward the surface of the Earth, or toward the center of the Earth. Okay? Something that I want us to think about here is it said this force acts along the line joining the two particles. Okay, so if I have two people, there's a gravitational force between these two people. Okay, some force between them. Do we see those two people like start sliding? No. Okay, hopefully not. But there is a force between them. Is the gravitational force between them going to go to the center of the Earth and then back? Is it going to be in like a wavy line? No. Okay, what I want you to understand is that if these two objects were to randomly start pulling toward each other, it would be in an absolute straight line, the shortest distance between two objects. Right? It's going to make that straight line path. That's all I wanted you to see about the definition here. We're going to look at the equation that goes with it. Okay? All right. You don't need to write this bullet. I'm going to talk about that here. Okay? I'm going to talk about these two things, but you can go ahead and write down this equation right here. Okay, I'm going to talk about these two things, but you don't have to have them in your notes. All right, I want you to take a look at this equation here. It said the force exerted by the Earth, that is Fg, right, our gravitational force exerted by the Earth, decreases with the square of its distance from the Earth's center. Okay, so let's think about what that means. If my radius here decreases, right, if my denominator gets smaller, what happens to my overall answer? It gets bigger, right? So as I get something closer and closer to the surface of the Earth or to the center of the Earth, my gravitational force increases. As I increase my denominator, right, if this goes up, what happens to my gravitational force? It gets smaller, right? So my force exerted decreases with the square of the distance. So as I get farther and farther away from the center of the Earth, as I increase my radius, I decrease my gravitational force. So we see that things on the moon have a much lighter or a much less gravitational force, right? That's why we say in space we're weightless, right? There's no gravity. That's because they're really far from the Earth. Okay? You'll even see an effect on gravity as you climb a really tall mountain. Okay? Anytime that you can get yourself farther away from the surface of the Earth, you'll see a drop in a gravitational pull. Okay, do we see that, how the math proves that now? Okay, so as your denominator, as your radius decreases, your gravitational force is going to increase. As your denominator or your radius increases, your force will decrease. So you need to be thinking, the farther away from the Earth, the less gravity you're going to have acting on you. Okay, so in this equation, F is really, I want you to think about it as Fg. Right? That's gravitational force. So you might want to adjust that in your equation sheet. I want that to make sure you understand that is the gravitational force, Fg. What's another way that we solved for Fg in previous chapters? Yeah, that's right. Mass times 9.8. Okay, this is the same force, except now we have a more complex equation to use for it. Okay? G is what we call the universal gravitational constant. And this value you will need to have down because you will use a lot. Okay, 6.67 times 10 to the negative 11th. Make sure you put that negative in there. This is a constant value, so it will be used and it will never change. So anytime you need big G in your equation, 6.67 times 10 to the negative 11th. Okay, M1 and M2 are just the masses of both the objects. Okay. Keaton, you all right? Okay. So if I look at my units for my constant, Newton, meters squared, kilograms squared. Okay, if I rearrange and solve for G, I would get force times radius squared over M1 times M2. Okay, that's where those units come from. So that means my force always needs to be in newtons. My radius always needs to be in what? Meters. And my mass always needs to be in kilograms. Okay, so in order for our G value to work, we have to be in those units. Okay, and a lot of times distances from the Earth could be given in kilometers, so you need to make sure we convert that to meters. Okay, want it in meters. And the last thing I want to tell you about this equation is, if we're comparing two individual objects, right, one person and one person, those are going to be both of our masses. If we're looking for the gravitational force of an object that's on Earth, one of the masses would be the mass of the Earth, and one of them would be the mass of the object we are comparing. Okay, and I will give you the mass of the Earth. It's another constant that we'll use a lot. Okay? All right, let's go ahead and try this one. 50-kilogram person and a 75-kilogram person are sitting on a bench so that they are 50 centimeters apart. What's the magnitude of the gravitational force each exerts on the other? So are we comparing the gravitational force exerted by the Earth, or we're between two objects? Good, we're between two objects. So we're going to use both of the masses of those people. No need for us to convert our masses because they're already in kilograms, which we like. What about our radius? That's right, very good. It should be 0.5 meters because it started out as 50 centimeters. So we want to make sure we convert that to 0.5 meters. A lot of you will forget to square the radius. I'm just telling you that right off the bat. Please make sure you are extra careful with that because that will be a big error if that happens. So where you're not up top. Please make sure that you're going to square that radius. Can we expect our force to be big here or probably pretty small? Really small, right? It's not going to be enough to move those people. It's not even going to be enough to feel it, right? Do I feel a gravitational pull between me and Sarah? No, right? We're not feeling, I don't feel like I'm leaning one way or the other even. Okay, we're not going to feel that. So it should be a very, very small force. Okay. Okay, Dan, what'd you have?
1 times 10 to the negative 6.
Good, and what's our units here? Good, yep. It's still a force, still a gravitational force, so it should be newtons. Okay, any questions? Let's go ahead and try this one. Okay, so do we feel like we're missing some information here?
Yeah. Yes.
Yes. What do we think we're missing?
The masses.
The masses. Okay, so here's what I'm going to tell you. Between these two situations, right, we have a gravitational force of 14 newtons at 10 meters. And between the second situation, when they move up, they change, right, they move somewhere. Is the masses of those two going to change? Are the masses going to change? No. So what we're going to do is we know the force, we know G, we know it's m1 times m2 over 10 squared. Okay, is this whole term, m1 times m2, is that going to change from the first situation to the second? No, so we're going to solve for this term as a whole. Okay, we don't have both masses, so we can solve for that term as a whole because m1 times m2 is not going to change between these two scenarios. Okay, that's going to allow us then to solve in the second equation for the radius. Okay, because we're not going to have our masses missing anymore. Okay, so we're going to solve for this whole m1 times n2 term. You can relabel it x if you want. I don't really care. We're going to solve for that term as a whole. So how would we go about doing that algebraically?
You mean making the m1 slash 2 1?
Yeah, we want to put that by itself. What should we do first? That's right. I would take 14 divided by 6.67 first. Move this g over. Okay. So if I've done that, right, I'm going to divide by g, and that gives me 2.09, or really 2.1 times 10 to the 11th. Okay, and that leaves me with m1, m2 over 10 squared, which is 100. Then we're going to take that times 100, and that would be the product of m1 times m2, which will not change between these two situations. Okay, so m1 times m2, I got to be 2.1 times 10 to the 13th, right? Okay, are we on the same page so far? Know where we're at? Okay. Can you give me a guess as to, do you expect the radius that we're solving for here to be larger than or greater than 10? It should be smaller. Why do we think it's going to be smaller than 10? That's right. Okay, our force started out at 14, force of gravity. Then our force of gravity got bigger, which means those two items have to come closer together, right? There'd be a greater gravitational pull as we decrease the radius between them. So we should be expecting here a smaller number. Okay, so now we know that our gravitational force is 56. G times 2.1 times 10 to the 13th over r squared. Okay, now algebraically we have to do something a little different because our variable here is on the bottom, but we want to get r by itself. So go ahead and solve the algebra to do that. Okay, again, I'm going to divide by g first. Okay, and when I divide that 6.67 times 10 to the negative 11, when I divide that over, this is what I'm left with. How do I solve this type of equation when my variable's in the denominator here? What should I do? That's right, I'm going to switch these two places. I switch these two places, right? The algebra that goes into it means I'm really multiplying and dividing, right? But simplistically, when my variable here is on the bottom, I'm going to switch these two places. Okay, which that leaves me with r squared equals 2.1 times 10 to the 13th over 8.4 times 10 to the 11th. And then at the very end, I'm going to have to do something else with that. I'm going to have to square root that number at the end. Okay, because I have r squared here. Manny, what'd you have? 5 meters. Yeah, Katie. Those are two values that you should have on your equation sheet. I'll always give you those. Those are unchanging, okay? So you should always kind of have those, and you'll use them enough that you'll start to get familiar. But those two equations along with G, I'll always give you those, okay? but you'll use them a lot, so I'd put them on your equation sheet. Okay. So here's the Earth. The radius of the Earth is from the Earth's core to the surface of the Earth. Okay, that's what the radius of the Earth is telling us. And it's telling us here that this spacecraft is orbiting 2 Earth's radii from the Earth's center. Okay, 2 Earth's radii from the center. So it means it's traveling a distance, right? Here's one radius worth of distance. Here's another. That's where it's orbiting. Okay, it just so happens to be the same distance from the Earth's center to its surface. Okay, so whenever we plug a radius into this equation, Fg equals g m1 m2 over r squared, whenever we plug in this radius, it's always the distance from the Earth's surface to the object. Okay, if we're ever comparing something to the Earth and we plug in the radius, it's always going to be from the Earth's center to the object. That's really important. Okay, you might want to put a note about that in your notes. Okay, when we use an r squared or use an r, it's from the Earth's core or from the center of the Earth to the object. Okay, if we're looking at something on the surface of the Earth, just like a person, right, then it's just going to be the radius of the Earth because that's how far it is from the Earth's center to the surface. Okay. So, we want to find the force of gravity here. We know G.
Wait, so it's when you use iron from the Earth center to the...
It's from the Earth center to the object, wherever that object is. Okay, so for M1, we'll use the spacecraft, so 2,000. For M2, what are we going to use? We're going to use the mass of the Earth for M2, because that's what we're comparing. Okay, so the mass of the Earth, which is 5.98 times 10 to the 24th, over the radius. Okay, so we want the radius from the Earth center to the object right out here. So what should we do to this value? Multiply by 2. That's right. So I'm just going to do it in the equation itself. 6.38 times 10 to the 6th. And then we have to make sure we square that whole term. Okay, after you multiply it by term. I'm sorry, after you multiply it by 2. Because we want the radius from the Earth's center all the way to the object. Okay, and it told us in our problem that it orbits 2 Earth's radius from the center. So here's 1 Earth's radius distance, and that's to the surface of the Earth. Here's another Earth's radius distance, which is out to where our satellite is, or our spacecraft. Okay, so algebraically, I like to start from this term and work my way over. Right? I would start here, work my way over, trying to keep as much in the calculator as I can. Okay? That's times 2. 2 times the radius of the Earth, and then square that whole term. I want you to go ahead and make sure that you're working this in your calculator. I want to see that everybody can get that to come out.